In this section, we'll be looking at the design and chemical structure of antagonists. So we will review the chemical design and function of antagonists. We will understand why they're designed in the way that they are and how they exploit binding groups within receptor binding sites to prevent receptor activation. Antagonists are designed to have the opposite effect on receptors to agonists. So they're designed to bind to the receptor, but bind to it in such a way that that receptor is not activated. So you can think of them as inhibitor molecules. They prevent receptor activation. Now, antagonists will bind to the receptor, but they won't activate it. And because they are bound in the same binding site as the natural messenger molecule can bind, the binding of an antagonist blocks natural messenger molecules from entering into that binding site. So this means that the natural messenger molecules also can't bind, and this will inhibit the action of the receptor. So the receptor does not undergo an induced fit process, and it therefore cannot be activated. Now, one approach that we can take is using a molecule that perfectly fits into the binding site. So for example, here we have a hypothetical neurotransmitter. Now, if we take this molecule and we make it a little larger, we say extend the length of this chain here, we can make the molecule go into a receptor binding site, but not activate it. Now, the reason for this is that the molecule is too long, this chain is too long here, and therefore it can have this electrostatic interaction with the group in the receptor binding site, but it can have this interaction without forcing the receptor to undergo an induced fit. So it's a perfect fit to the binding site, and so it can bind without activating the receptor. Now, one tactic that we can use is to use the natural binding regions to mimic the binding of the natural substrate, such as we have here. But we can then tweak the molecule to make it larger so that the protein doesn't have to have an induced fit to allow the molecule to bind. Now, we need to make sure that the antagonist has stronger binding than the natural messenger molecule. Otherwise, it could be outcompeted by the natural messenger. Now, if we have a molecule that has a perfect fit into the binding site, this will result in either minimal or no induced fit and no biological activity at that receptor. So our objective with an antagonist molecule is to have a molecule that can bind very strongly to the receptor, but do so in such a way that no induced fit occurs. If no induced fit occurs, the receptor is not activated. Now, another approach that we can take is to use different binding regions within the receptor binding site. Not only will binding of an antagonist in this way inhibit the binding of the natural messenger, but it will also result in a different induced fit. This will deactivate the receptor. So for example, here we have a natural messenger molecule bound into the binding site of a receptor. Now, it uses binding to specific groups to make sure the correct induced fit occurs and that the receptor is activated. So for example, here we have hydrogen bond formed between an OH group in the receptor and an OH group on the molecule. We have a van der Waals interaction here between the six-membered ring and a van der Waals binding region within the receptor, and we have an electrostatic interaction here as well. Now, when the induced fit occurs, this induced fit happens in such a way that the receptor is activated. However, if we put in an antagonist that uses additional binding regions, such as an additional van der Waals binding region here, we can cause the receptor to have a different induced fit. Now, you can see here that the binding site looks very different to the binding site up here. And this different induced fit won't cause the receptor to be activated. It hasn't changed the shape of the receptor in the correct way. And so it will deactivate the receptor and stop it being activated. So we can either produce a molecule that will be a perfect fit to a receptor binding site, and therefore it won't require an induced fit for that molecule to bind. Or we can take advantage of different or additional binding regions within that binding site to give our receptor the wrong induced fit. And in doing so, this will deactivate the receptor. Now, just to come back to the example that we had much earlier in this lecture series, here are two examples of a molecule bound into the B1 receptor. Now, in grey, we have salbutamol, and the grey receptor corresponds to the salbutamol that the receptor has bound into, and this acts as an agonist. Now, the cyanopindolol, which is in cyan, acts as an antagonist, and the receptor is shown here in cyan. Now, what you can see is that the salbutamol, the agonist for this receptor, is smaller than the cyanopindolol. The cyanopindolol extends further out from where the salbutamol would be, and it's this size difference that allows the cyanopindolol to act as an antagonist. It binds into the receptor, but it binds in a way that doesn't activate it. The salbutamol, being smaller, binds in a way that activates the receptor and allows it to have the correct induced fit. Now, I'd just like to show you another example of an antagonist. Now, you don't need to remember this, but you need to make sure that you're comfortable with the concept of an antagonist and the way in which it's designed and what it's designed to do. And so I'm going to use this example just as an illustration to illustrate the points in the previous slide. Now, estradiol is a steroid hormone, and this is involved in the growth and development of several different types of tissues. Now, it's able to cross cellular membranes, and it binds to an estrogen intracellular receptor. So it binds to a receptor inside of the cell. Now, this is what the molecule looks like when it's bound into the receptor. So the molecule here is shown in blue, and the receptor is shown in green, red, and blue. Now, if we have a look at how the molecule is actually binding, what we can see is that the molecule is able to form hydrogen bonds with multiple groups in the receptor. It's also able to form another hydrogen bond here. And this whole molecule, this part of the molecule, is very hydrophobic. So we call this a hydrophobic skeleton. Now, hydroxyl groups form bonds with 3 amino acids in the active site. So what we can see here is this hydroxyl group here and this one here form hydrogen bonds with this histidine, this glutamic acid, and this arginine. The hydrophobic skeleton is able to form van der Waals and hydrophobic interactions with the binding site. So we can see that there are a number of different interactions holding this molecule in place. Now, when the estradiol binds to the estrogen receptor, this results in a conformational change and allows the receptor to become activated. So here we have the estradiol and a binding site on the estrogen receptor. The estradiol binds into this binding site, and a helical region from the protein is able to fold over and cover the binding site. Now, this exposes a hydrophobic region on the receptor and allows it to dimerize with another receptor. Now, this results in the exposure of 2 regions on the receptors, and this allows a coactivator to bind, and it's this coactivator that binds and ultimately allows protein synthesis. So it binds, it can perform transcription, and this enables the synthesis of proteins. So it really is the binding of the estradiol that initiates this entire process. Now, raloxifene is an antagonist for the estrogen receptor, and you can see the molecule over here. Now, this molecule binds in the same way as the estradiol. So what we can see is that we have 2 hydrogen bonds here between an OH group and amino acids within the binding site, the same as we have with the estradiol. We also have a hydrogen bond between the OH group and a histidine, and we can see that here. So we're exploiting all of the same binding interactions. However, the raloxifene also has a long tail coming off the molecule, and this forms an additional hydrogen bond with an amino acid within the protein. Now this chain here forms this extra binding interaction, and it blocks the folding of the helical section. So if you remember back to the previous slide, the first thing that occurred after the estradiol bound was the folding of this helical section of the protein. Now the binding of this antagonist to that receptor inhibits that folding of the helical section, and this prevents the dimerization and it inhibits the cofactor binding to the protein. So what it means is that this antagonist is able to stop the protein production, and it does it by binding with the same binding interactions and some additional interactions to interfere with the function of the protein itself. So now that we've reviewed the concept, molecular design and function of antagonists, we also need to note that just like with inhibitors binding to enzymes, antagonists to receptors can also bind at allosteric sites. So they can bind at binding sites in the receptor that aren't the same binding site as for the messenger molecule. Now these are called allosteric modulators. Now what we can see here is an allosteric modulator. This is able to enter into an allosteric binding site on a receptor. When it does this, it can also have make the receptor have an induced fit, and that reduced fit will alter the structure of the binding site. So it's not always the case that antagonists are used to block the binding of the natural messenger molecule directly. They can also be used as allosteric modulators to change the structure of the receptor in order to make the binding site unable to accommodate the natural messenger. Now with antagonists, this can lead to another effect. So if antagonists bind to an allosteric site that is near the natural messenger binding site, they can also provide an umbrella. Now here we have our antagonist that's binding into an allosteric site that is close to the binding site for the natural messenger molecule. Now through what's termed the umbrella effect, they can partially block or completely block the binding site for the messenger molecule. So in this case, the antagonist is not acting to change the structure of the binding site, but it's physically blocking it by binding to a very near site to the binding site and then blocking it with functional groups or large chains or rings built into the antagonist. And so the antagonist can act both at allosteric sites to make the receptor have a different induced fit, which alters the structure of the binding site, meaning it's unable to accommodate the natural messenger molecule. Or the antagonist can provide an umbrella effect. This is where they bind adjacent to the natural messenger binding site and they physically block access to that site. And this stops the natural messenger molecule from binding into the binding site and therefore prevents the receptor from being activated. Now in the next section we will review partial agonists and inverse agonists. Now these are drug molecules that the effect of which lies somewhere between the two extremes of agonist and antagonist.